Yeah, I'm very happy to introduce Rama Govindarajan, our speaker for today. She is basically a fluid mechanics person who leads the monsoon group here, or maybe one of the people involved in the monsoon group here, and also works on cloud physics. And lovely person, loves to talk to students. So please feel, I guess I'm just offering her up. You feel free to talk to her. And she's done a lot to get climate science and issues of climate into public conversation. So over to Rama.
Thank you, Kripa, for that. And thank you. And sorry for the glitch over here. So today we're going to talk about cloud physics, and I'm going to try to convince you that it's hard but fun. Okay, so this is a photo of the Earth taken from a satellite, and you can see all the white stuff is cloud. So you can see that about 70% of the Earth is covered by cloud at any time. So we'll just run this movie over a few years. So you can see, in fact, you can see the monsoon clouds over India every year. It comes up and down. Do you see that? So the point is that clouds are big, clouds are everywhere. And at any time, there's a lot of cloud over the Earth. And yeah, you might wonder why it, covers India, but not the Sahara, which is at the same latitude. Okay, so what is cloud formation? So you can imagine that there is some water body here like an ocean, and there's evaporation due to the heat from the sun. And these are blobs of, warm, moist air. So the air contains water vapor, and these blobs are evaporating off the ocean, and they're climbing all the way up, and then they go all the way up and become a cloud, right? Now, what happens is, like, let's do it in a little more detail. So you have the water body here. The temperature above us is falling as a function of height, right? Yeah? Okay, how many of you were in a plane recently, like last 10 years? Lots of you were in a plane. And what was the temperature outside where you were flying? What? Cold. How much? Any numbers? Pilots announce the temperature, right? Next time, listen. Okay, any guesses? Huh? Any guesses about the height you fly at? At least, like, say with them right or wrong. 100 kilometers? Wrong. What? Higher, lower? Higher. I'm flying at 10,000 kilometers above the Earth? No. How thick is the Earth's atmosphere? By the way, those space shuttles, when they go around the Earth, they are at about 60 kilometers above us. So the space shuttle can be much closer to us than Mysore is. So yeah, that's outside the atmosphere. So the real part of the atmosphere where you can breathe or do something. Already, in Himalayas, you can't breathe much, right? You can't breathe too easily. How high is the Himalayas? 8 point something kilometers. So you're at the edge of you're already in very thin atmosphere. And you know that an airplane cannot fly if there's no atmosphere, right? Yeah, so you fly at around 10 kilometers. That's the order of magnitude. And the temperature there is minus 40. So the point is that, like if I'm able to go vertically up 10 kilometers, just 10 kilometers, I'll be at minus 40, whereas here I am at 30 or something like that. So I can have a 70-degree drop by just climbing 10 kilometers, which is a shorter distance than here to Jalahalli, right? Except that I can't go vertically so easily. So the point is the temperature is much, much lower. And there is this dotted line you see called the lifting condensation level. That can be different depending on the situation. But above that, the amount of water vapor that's carried in these blobs is enough to start condensing. So why is that? Why does condensation happen? It's cold enough, so you reach saturation, right? with the water vapor you have. That's perfect. So then you start seeing the cloud, you start seeing little water droplets forming there, and there are little aerosol particles, and you have water droplets condensing onto them, and that's how a cloud forms. Okay, so I told you a story of how a cloud forms. So is there anything to study in this? Like, why am I doing research in cloud physics? I already told you everything about a cloud. Anybody can come up with anything we need to understand. Any guesses? It's okay if you make a wrong guess. Weather forecast, yeah. So why do I need, I already know the answers about a cloud. So why do I need to do research on it? I can already forecast it. Excellent, excellent. So like you agree that there's a lot that's not understood, right? Anyone else wants to add to this? Anything else we don't know about clouds? Yes? Yes. Yes, yes, very good point. Any others?
There's a lot of turbulence in the atmosphere as such, so it kind of affects the cloud movement.
Very nice. We'll be talking about that. Anybody else? Okay, great. So I think everybody is in broad agreement that there are things still to study here. Okay, so here is a bumblebee, and I'm going to divert from a cloud for 1 second, because like I'm an aeronautical engineer, and when I joined the aerospace program, this is the first thing that people tell you, that if you're an aero engineer and you can do the lift calculations and so on, you know very well that a bumblebee cannot fly. So all logic tells you that a bumblebee cannot fly, and this is now a competition between logic and the bumblebee. And who wins? The bumblebee, right? And so it's able to fly because actually it didn't know about this logic. So yeah, so that's like bumblebee logic. So this happens to a cloud also. So it's just, why is our logic failing? We did our calculations based on a fixed wing. That's what an aeroplane has. It has a fixed wing. Whereas the bumblebee flaps its wings, it can change the shape of its wings. It can do something while going forward, something else while going back. It can do a whole variety of things which give it enough lift. Right? So like, it's just that we didn't know the science behind it, so we put logic on it. Right? So now the same thing happens in a cloud. First of all, like, should a cloud form at all? Plain simple logic will tell you it should not form. So let me show you why. And I may not get to the end of my talk, but it will be, so this is smoke coming out of a chimney. Okay, everybody's seen that. And as it comes out here, it's pretty black in color. Can you read at the back? Yeah, it's black in color. You go up, 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 it becomes lighter, lighter, lighter. And like here, it seems to be gushing out. Here, it's slower, slower, slower. And then after some height, it's not very smoke-like, right? It's very, very mild. Whereas, and the same thing I told you happens to a cloud. Like here's the ocean and here's the blob, which is going up. How come it can take its water vapor 10 kilometers up when this guy cannot take its suit 10 kilometers up? So like everything else dies very quickly, and by all logic, it should also not, a cloud should never ever form, right? So what's happening is that in a chimney smoke, there is this angle. That means the chimney smoke occupies a greater and greater volume as it, greater and greater area, cross-sectional area as it goes up. And that happens because air from the outside is pulled in by these turbulent vortices that are here. All these flows are very turbulent. So then like when you mix it with fresh air, you share your momentum, you share everything with the fresh air, and you die effectively. Whereas this blob, which is rising as a potential cloud, it effectively builds a wall around itself. And the outside air does not come in, although it's also a turbulent quantity. So this I'm not going to answer here. I'll just leave it as a thing, like a cloud should form at all, because we don't have time to talk about that one. But if we agree that a cloud exists somehow, so that's like the first question. Like, I mean, we shouldn't think of it as a bumblebee thing. There's something we're missing here. So if a cloud exists somehow, logic tells me that there should never be rain. So the reason is that, so we talked about this thing reaching the lifting condensation level, right? So it reaches this condensation level, and above that condensation starts happening. And then like you make little drops of 10 micron in size. Now those 10 microns, so like here's where this happens. So the little aerosol particles are about 1 micron. The water droplets started collecting on this. And by, the surroundings being super saturated, and water vapor was going into this droplet, diffusing into this droplet, and the droplet grows bigger, it reaches 10 micron. Once it reaches 10 micron, the growth becomes very slow. So how big is a raindrop? Order of magnitude. Huh? How big is it? 1 micron? Any thoughts? You've seen rain, right? What is your concept of how big it is? Any guess, like order of magnitude guess? Half a centimeter diameter? Yeah, those are like big raindrops. Let's say order of millimeters. Huh? What? 1 to 2 millimeters. Yeah, very nice guess. So everybody agrees it's order of millimeters? Yeah, great. So like how many 10 micron droplets should join together to make a 1 millimeter droplet? One millimeter droplet, how many should join? Why did you get 1,000? 10 micron is 10 power minus 6 into 10. Okay. Okay. So here I have a little droplet whose radius is 10 micron. Here I have a raindrop whose radius is 1 millimeter. 100. 100 droplets joined together, it will make this. It's volume, no? So how many should join? How many should join? 10 to the 6. That's like 1,000,000, right? So this every little raindrop. So I told you that after this size, just by water vapor coming in, it can't grow. It can't really grow. It will be very slow. It will take 4 months or 6 months to reach 1 millimeter. The only way it can grow is by many of them attaching themselves to each other. That means coalescing. That's the only way to get that. And you can imagine that in every 1 millimeter raindrop, those are the tiny ones that she talked about, not the big ones that you said. So there'll be 1 million of these 10 micron droplets who coalesced. So like 1 million coalescences should happen for one raindrop to happen. And if you do like normal logic, like what do we do? What do we call logic? So we can have these, we can think of these droplets as wandering around in the turbulence. So suppose I say they're all doing some random motion. Then you've studied kinetic theory of gases. Yeah, you've talked about collisions and things. You know how to calculate a mean free path, right? So you can do something like that for this thing. Calculate a mean free path. And you'll see that the water droplets are actually very dilute in a cloud. And by, like they have to come and dash and then coalesce, it's impossible by that calculation. That calculation makes it completely impossible to do it. Except when there are a few drops who are already, like that big one. So there are a few big drops and they will fall faster due to gravity than the others. And these tiny drops are falling very slowly. By the way, did anybody worry about why a cloud doesn't fall down? You never worried? Water is how much denser than air? Huh? Huh? When it's raining, yeah, but You agree that 70% of the earth is covered by cloud and only in a minority of those clouds there's rain. Then like, why doesn't it fall down? Any answers? Water is how many times denser than air? What's the density of water? 1000? Excellent. And air? 1 kg per meter cube. So this is 1000 times heavier than air. Like if I leave a water droplet here, it will fall or no? Okay, so why isn't a cloud falling?
Because they are not all combined together, right? When they combine together, they do fall. But because they're so dispersed and diluted, the air is able to hold.
Air doesn't hold them up. Okay, technically they're actually falling, okay? They're actually falling, but their terminal velocity is so small. And the minute so they're falling extremely slowly. You can calculate the terminal velocity for a 10 micron drop.
Yeah, it's like a feather falling.
Yes.
Constantly falling, but
Yes. So in some sense, the air is holding it up in the sense that it's giving a drag. So some amount of, its acceleration is reduced by drag and it falls very slowly. And the smaller it is, the bigger the drag is in proportion to the gravitational force. So it is like coming down slowly. And as they leave the cloud ka base, they're going to evaporate. They're going to evaporate. So like you may not see them. They'll be so tiny and at the same time they're evaporating. So yeah, that's the reason. But let's go back here. So if there's this big drop by gravity, it can collect. So like, first of all, you need some big drops, right? In order to, fall faster than small drops. Big drops fall faster because the terminal velocity is bigger. And as they fall, they can dash against the little ones and collect them. And not every collision will result in a coalescence, but they can collect quite a few. Okay, so that we know that if there are some 100 micron drops, they can quickly grow to 1 millimeter and become a raindrop. So they have that potential. So like, in which cloud do you put enough big drops? That's the question. And here, like, turbulence is supposed to help you. And we will ask about turbulence. We know why it does things to bigger drops. We don't know why it does things to smaller drops, which I will address. Any questions so far? Anything at all? Anybody wants to discuss turbulence? Anybody has some concept of turbulence, or shall I give a small explanation? Small explanation? Okay. So here it is. Anytime you have a cloud, most likely it's turbulent. Most likely it's turbulent. So like, when the pilot puts on the seatbelt sign, okay, look out of the window. How many of you travel by the window seat? Everybody likes window seat, right? So now you look out immediately. Don't just wear your seat. Wear your seat belt, but then look out of the window and you will see that you'll often enter into a cloud. So you can have like rarely clear air turbulence, but a lot of the turbulence when you wear your seat belt and all is because of clouds, which is why in the monsoon season, like that's it. You get into the flight, wear your seat belt and just hold on to the seat till they land, right? It's always bad in the monsoon season. So yeah, so the moral is a cloud is turbulent. And yeah, so what is turbulence? You know that it's some kind of random motion, of the fluid, whatever it may be. In this case, it's air. It's just some random motion of the fluid. So it's actually a nice thing, turbulence, because turbulence is what brings us rain. So next time, somebody tells you turbulence is wasteful, turbulence dissipates energy, like this and that, like don't listen to them. There are good sides of turbulence. Okay. So another good side of turbulence is right in your washing machine. So who's seen a top load which goes round and round, or even a front load which goes round and round? Everybody's seen it. What are we doing? We are putting energy into the drum, and the drum is going round and round, right? So like imagine if all the water inside just went in solid body rotation. Okay, if it went in solid body rotation, your clothes are not going to come out clean. You need like large amounts of mixing, large amounts of pushing around. And this is what turbulence does. You're trying to put it in solid body rotation, but it creates vorticity like this. So these are all, they're of all scales, all sizes. It's like long noodles everywhere in the flow. So if only you could see the flow. For example, if you could see the flow above my head, you'll already see turbulence. Did you see Schlieren in the experiment? Go look at videos of Schlieren. So you can already see that right now, because I'm warmer than the room, I'm emitting a turbulent cloud thing above me, turbulent plume. So that contains all these vortices. So we just don't see rotationality, but it's everywhere. Okay. And it can be very, very big things. What is vorticity? It's basically the curl of the velocity vector. So you can imagine that these are rods, like noodle-like things where the air is rotating like this. Got it? And each vortex, each noodle is telling all the others where to go. It has forcing on the others, and they die, they get born, they form, they die, they become larger, they stretch out and become thinner. All kinds of things are happening. They go into crazy knots, then they unknot. All kinds of things are happening as you talk. So this is basically the picture of turbulence I'd like you to have. Just think of it as a bunch of vortices. It's like a, a bowl of noodles, except the noodles are different powers, different rotation rates. They're all rotating like crazy. They're doing all kinds of things, and they don't last forever. They are born and they die. Okay, so now the point is that this big cloud we can never solve for. So we must solve for all of this in order to understand the cloud. So in order to do that, we have to forget about the big scales. Although the big scales tell the small scales what to do, and the small scales tell the big scales what to do, we have to decouple. We don't have a choice. We decouple and we're going to solve for the small scales. So in order to understand rain formation, so this is the question we're going to answer now. If the cloud exists somehow, tell me like how I'm getting rain, and how does turbulence help this process. So that is like from 10 micron to grow to 100 micron, you need turbulence. So this is the moral that we are talking about. Okay, so how do we solve it? Any thoughts on how to solve it? How do you solve any problem that's given to you? Observe, that's a good one. Understand? So, but if I want numbers, like, okay, so I'm saying like, let me tell you another fluid mechanics problem. Like I have a big tank of water and I'm opening a little hole at the bottom. And I want you to tell me how much is the flow rate. How will you obtain it? In which equation? Yeah, we can get the variables that are involved. In this thing, there is air. Air has, a density and other properties, viscosity and so on. It has a velocity at each location and time, which is one horrendous thing. And all of them are forcing everybody else through this magic thing called pressure. So pressure can, be felt a distance away, and you can have that. So there is all this happening. And there's also vorticity can push other vorticity by the Biot-Savart law. Have you heard of that one? No, you'll be studying it. Promise. Okay, so I just don't want you to understand anything about this, but these are the equations. It's effectively a force balance. This is what, it's effectively Newton's laws, right? When you're pushing something and something moves, it's Newton's laws. So like this is a complicated version of Newton's laws, which is for fluids. I don't need you to understand this. And there is this external force which comes because there's temperature variations, water vapor variations, so many other equations we have to solve for the air. And there is this quantity called Reynolds number. So even if you don't understand anything in this talk, or you don't like anything in this talk, please take home this concept of the Reynolds number. So what is the Reynolds number? The Reynolds number is a ratio of inertia to viscosity in any fluid. Okay, it's a ratio of that. And what happened? This U is like any velocity scale, typical velocity scale in the cloud. So in clouds, hurricanes, big clouds, what would you say is the velocity? What is wind speed? Any estimates? You know how much is wind speed typically? Is it faster than a car, slower than a car? Slower than a car. How much? Okay, so suppose I tell you, like, okay, tell me how much is the speed of a car? 40 kilometers per hour. Everybody agrees with that? Okay, go home and see like what is the typical velocity scale in a cloud. Go home and check on this right away. Length scale, like it's how big is a cloud? Any thoughts? Thoughts? Yeah, like on the earth, you saw like it could be 10,000 kilometers, right? It was stretching from this end to that end. Yeah, it depends. So like different clouds are of different length scales, and you can actually, clouds actually merge with each other. These are all things we don't understand, like how big does a cloud grow to? Okay, but yeah, it can go from, you know, maybe 100 meters to like 10,000 kilometers. So it's a very, very big scale. And now like there are these teeny tiny water droplets. Now, if I'm going to solve for each water droplet, it's a horrendous set of equations. Like just note the integral here from 0 to t at every time, okay? Divided by root of t minus s. So you have to integrate it from 0 every time. So like every teeny tiny droplet, I have to keep track of her or his history and follow that droplet and each time calculate this. So to understand where each droplet is at a given time, I have a very, very hard time. So like you can already see this is an incredibly big problem, right? So what do we normally do when we solve? Hey, Kripa, tell me when I have like 5 or 10 minutes left. So we know the equations. So normally we say, if I know the force balance equation, I can solve it and get the answer, right? And now we know the equations. Okay, they're complicated equations, but we have computers which can solve. By the way, like this equation, do you think it's an ordinary differential equation or a partial differential equation? Partial, why? Yeah, which are the variables? T is time. And this grad is what? In space. You've seen a bunch of grads in this thing, right? In this course. And so those are like functions of, those are in X, Y, and Z. You're taking gradients in X, Y, and Z. So there's like 4 independent variables, X, Y, Z, X, Y, and Z in space and time. So these are very complicated partial differential equations. Okay, but still like the computer is supposed to be able to solve them. This Reynolds number is very big for clouds, and that's going to be very, very important for us. Okay, so now we say, okay, we know all the equations, there's no magic here. And now we had these partial differential equations, right? Computers normally don't handle partial differential equations, but they can handle discrete difference equations. So all the derivatives I can write in terms of some Taylor expansion. Okay, and then I can feed it to the computer, saying solve for u in every place when you know the equation. So then you have to apply boundary conditions. You all know what boundary conditions are, right? So technically around each droplet, I should give its rotation rate and its velocity as the boundary condition. So there are boundary conditions at each droplet. And then like if I can choose a small enough step that my Taylor expansion is going to work, then I'm in business, right? So this is how it is, except that it doesn't work that way because you can do this solution very well for small Reynolds number, small inertia. That means teeny tiny things which move slowly, where the typical velocity and the typical length scale is small. But when you yeah. So when you're talking about a thing like a cloud, a very big one, you can't actually solve it. So you can only solve for smaller Reynolds. Here I've given you solutions for 2. I'll come to what they are. One is at low Reynolds number, one is at high Reynolds number. What I call high is like may be 2 orders of magnitude smaller than in a cloud. So this is like by some world record computer, which has calculated turbulence, and even that is way smaller than a cloud. So like if I know low Reynolds, high Reynolds, can't I extrapolate the answer to even higher Reynolds? The problem is I cannot. And the reason for that is turbulence is intermittent. How many of you heard of fractals? 1, 2, 3, 4. Okay, what do you know about fractal? You can sit down. Just talk loudly. Excellent. So it's a self-repeating pattern. Anything else you know about it? Huh? So, yeah, it has something to do with chaos theory. Anything else? Anybody else who has a thing about a fractal?
What I have observed is that snowflakes
Mm.
have infinite perimeter but finite area.
Excellent. Excellent. So you can say that it's not a one-dimensional object because it has an infinite perimeter, but it's not a two-dimensional object because it has 0 area. So it has somewhere between 1 and 2. It has a fractional dimension. Okay, turbulence is like that. All these vortices occupy fractional dimensions. They don't occupy 3D space. And so that's why I drew a pulgobi here. Actually, I cut out a picture of a purple cabbage to match the purple here. So you can see right away that the cabbage is not 3D, right? What's your guess for its dimension? Between 0 and 1, 1 and 2. What's your guess? Okay, like go home, take your cauliflower, preferably a purple one, make a cut, and do a box counting thing and find out the fractal dimension of a cauliflower. Okay, it will be hopefully somewhere between 2 and 3. I haven't done this exercise. Like I mean, I'm just giving it to you to do. Okay, so turbulence, the vortices in turbulence are like that. So what Rajeshi did for you guys is that he actually colored things of high vorticity in shiny color in this and this, except that these vortices, there's a scale difference. Like these are actually way more shiny than these. But do you see that the pattern is entirely different in low and high Reynolds number? These are very streaky structures. It looks better on my computer. These are streaky structures, whereas these are quite fatter structures. So this is why you can't, and that means that at higher and higher Reynolds number, you have thinner and thinner, more and more powerful vortices who are occupying less and less dimension as you go down and down in scale. So this thing, this thing makes it it's practically impossible to extrapolate. Now, if I am a tiny droplet and I am 10 microns and I have every ambition to get into turbulence and become a raindrop, right? That's my ambition. Like, why do I want to just stay in a cloud and dry off? I want to do this. Then like, I will have to make use of these vortices. And we'll see how. I'll have to make use of these vortices and I'll have to, dash against my friends much more than some mean free path calculation will tell me. I have to dash very, very fast against them, right? So this is my ambition as a raindrop. And how do we do that? So like you see that this, but if these vortices are, whoops, what's happening to this? If these vortices are so teeny tiny, and then if I write difference equations, I should draw little boxes very much smaller than these vortices, right? Otherwise, I won't be able to solve for the vortices. Like if my box is this big, then I'm in deep trouble. And you see that as the Reynolds becomes more and more, the structures are very, very, very fine and tiny. So I have to draw more boxes. So that's what it's telling me. So because I have to draw that many boxes, no computer in the world can solve for a cloud. So a cloud, the best simulation in the entire world today can put 16,000 little boxes on one side. And that corresponds to something like a 2-meter cube box in a cloud. So I can solve for a teeny tiny box in a cloud if I have the world's best computer, which I don't, right? So that is how it is. So we cannot solve for the entire cloud. So all the big scale vortices are forcing the smaller scales, but there's no way I can get that. So that's where it stands. And this is the best simulation we can do. So we just put some toy forcing, which we believe is kind of like the big scale. And then we solve for the small, teeny tiny box, which is just 2 meters. And we agreed that a cloud can be, thousands of kilometers. And that's if we have the world's best computer, which we don't. Now, even if I put all the boxes, like 16,000 boxes here to solve for the flow, these grids are so big compared to the droplets. In fact, I've expanded what it does. So there's no way I can put a grid around each droplet and give the boundary conditions there and things like that. So the moral is that we can't solve it by brute force on a computer. We have to use brains to simplify the problem. And I'll just give you one example of what we simplified. So is it okay so far? Anything you don't understand, tell me. I really don't have to finish this talk, but I want some discussion or whatever out of this. Anything you want me to repeat, you didn't get?
Why don't we go smaller? Why don't we take like a 500 meter or like 1 meter box, 10 centimeter box?
We can.
Then wouldn't it be more?
We can, but in the 10 centimeter box, we're losing a lot of the physics which is coming from the big scale. Because now we're pretending that this is the Reynolds number. So we're actually solving for a small Reynolds number. We're saying there's no forcing from the big scales. The biggest vortex is 1 meter. And because the biggest vortex is 1 meter, this is what will happen. And we may get exact answers if the biggest vortex was 1 meter. But we have vortices of all sizes who are forcing these guys and being forced by these guys. So we're missing all that interaction which is happening. Okay, ask more questions. Otherwise, I'll point you and ask you to give my lecture. Ask more. Okay, we'll continue. Okay, so we have 10 to the power of 13 because the aerosol particles are 1 micron. If I want to solve for the whole thing, I need a grid which is 10 to the power 13. And which is the biggest grid I said we have? 2 meters, but how many boxes in the grid? 16,000, right? Where is 16,000 and where is 10 to the power 13? Right? So we're not there. And you have to take a cube of that because there's in every dimension you have that many. So 10 to the power 33, 39, right? Yeah, forget it. And then in each cube, there's in each centimeter cube, there's 1,000 droplets. So yeah, we're reaching. And on top of that, there's so many other physics going on. There's these clouds are aggregating on the planetary scale. The raindrops are evaporating. Because they're evaporating and condensing, there's latent heat given. That latent heat can make the air lighter, heavier in different portions. That can convert itself to kinetic energy. So you can get more vortices from there. And then clouds are forming and unforming and dying. Then there's other things which are, changing the answer here. So everything is messing up with everything. And it's an incredibly hard problem. So have I convinced you it's hard? Yes. Have I convinced you it's fun? No. Okay. So how do we handle this? So we have a strategy. In our strategy, we first try to do pen and paper work. We try to do the easiest thing we can and then make it a little more complicated, solve it analytically or numerically, and then do these larger simulations. And we are very, very happy when this teeny tiny pen and paper work gave us an answer which the large simulation gave us. So if we understood something and the big simulation was only a confirmation, then we get really, really happy that we've actually pinned down some physics with pen and paper in this hard problem. And that's the fun part. Oops, you wanted to take a pic? You have the record of this whole thing. So now the point is that in all this complete mess, we're going to take one vortex, which is the building block of turbulence. One vortex, which could be stretching, which could be becoming fatter, whatever. And we're going to look at everything around one vortex, and there we can do an analytical approach. So here is one vortex, that little black circle you see there is one vortex. And in that vortex, we put green particles, green water droplets and red water droplets for a certain reason. I want to show you that the green water droplets are born lucky, and I'll tell you why. So, this simulation also I'll show you. It's a movie which Jason, who's visiting here, made this movie. So the moral basically is that if you take any turbulent flow and look at, the vorticity looks like this. This is just a cross section. And all these vortices are typically circular blobs. They could be funny shaped also, but very often they are in circular shape. And they have a Gaussian cross section. So the vorticity comes down like this. So this is what these vortex blobs look like. So we're just taking one of them and putting a whole bunch of teeny tiny droplets around it, which is what happens in a cloud. And then we're going to ask what happens. So like typically, what do you think will happen? If I have these droplets are very heavy, right? Compared to air, right? And the vortices are made of air, right? So now if I have a spinning bunch of air and I put droplets there, what do you think will happen? What? Okay, technically, yes, but these droplets are too few in number. They occupy like 10 to the power minus 6 of the volume. So they can't have much effect on this very powerful vortex. So the droplet can't do much to the vortex. The vortex can do something to the droplet. What do you think it will do? 10 minutes more, great. What do you think it will do? It will go round and round. The droplets will go round and round. And in that process, they'll centrifuge out, right? They're heavier. They're going to centrifuge out. So that's what's going to happen. That's basically, if you've got this one thing, then I'll be very, very happy. So these droplets are going to centrifuge out. And as they centrifuge out, they have chances of dashing against other people, right? So the ones very close to the vortex will be centrifuging out rapidly. The ones far away are going to be centrifuging out slowly. And so the guys who are inside are going to be the lucky ones. And Ravichandran, as I'll show you in the next page, found this very nice property that only these droplets who are inside a particular radius near the vortex, they are only the lucky guys who can dash against others by moving out. The others can slowly centrifuge out, but they'll never cross anybody. They'll never walk past anybody. So that is this special diameter. So let's now just run this code, run this thing. This simulation is not even Navier-Stokes. We've run Navier-Stokes here just to demonstrate, but we didn't need to. We could have run the equation I'll show you you see that centrifugation, right? So you see that the green guys are all collecting in a very thin strip. And then these blue ones are the ones who were born with some green blood in them. So if a little bit of green blood was there, then we color those guys blue and we color everybody else red. Okay. Now, how many big drops do you see? Quite a few, right? And how many red big drops do you see? What? Do you see any red big drops? In some other pictures, we have a few, but primarily, everybody who's big has green blood in them. Agreed? Yeah, there's no drops there. It's made a void. All the drops have centrifuged out of there. Which? No, that's a vortex. That's the vortex. That little black guy is the vortex. So these things are just centrifuged out of there and they made a void. So this is what we believe starts the process of making the droplets. And here is just a simulation by Jason on two-dimensional turbulence. So you see even there, these voids are created. And they're not quite circular because many vortices are interacting with each other and all. But you see how the droplets move. So like these voids are created. Okay, so I just showed you one example of something where actually his real name is Ravichandran. He's now faculty in IIT Bombay, but all of us call him Kroor. Like we never remember his real name. That's why I wrote his real name down. So yeah, so Kroor actually wrote down the equation for this vortex, and then he chose a very nice length scale to non-dimensionalize the equation, just to scale out the equation. And he got these two cutie tiny equations, which are both like ordinary differential equations in time. Okay, and then he could solve some instances of it by hand, or you can solve it on the computer. And you just solve these two teeny tiny equations, and it's equivalent to solving Navier-Stokes near vortex for these particles. So this is for each and every particle, how it goes out. So that is the simplification. That's the kind of thing we aim at, like pen and paper work with simple equations. And this special radius I told you, and this dashing against each other, we call it caustic. So this is one example. And based on that example, we tried to work out which cloud will rain. So we said a cloud will rain if it has enough voids and enough people have chance to dash against others. So based on that, we gave a minimum Reynolds number just by hand waving argument, but there's a long way to go to understand which cloud will rain. Okay, so do I have like 2-3 more minutes, or shall I skip this? Okay, okay, so I have time. Okay, has anybody seen these clouds? Okay, so the hard part of the lecture is over. Now is the fun part. Yeah, anybody seen these? They call mammatus clouds. Okay, so what people say is that these clouds are they're serendipitous but not rare. Can you explain what that means? Any thoughts on what that means? Who knows serendipity? It means by chance you see them, right? You can't predict when you'll see them. You can't prepare to see them, but they're not that rare. If you look out for them, you'll see them. So how would you describe this cloud? Like it has some blobs, like pendulous blobs coming down, right? These are the mammata. And that is some picture from the internet, picture from the internet, picture from a newspaper in 2018. And this is a photo which Sid took on 20th May. That's like less than a month ago. He took it just outside ICTS. Were you guys here on 20th May? No. So you missed this mammatus cloud. And the same mammatus cloud, Debashish took a picture in IAC and sent me, because they know I'm crazy about mammatus clouds. They keep sending me pics. So yeah, like this was the exact same cloud at the same time. So I got these WhatsApp photos from both of them at the same time. And then there's another friend I have called Laurette who keeps looking for these photos and sending me. So like if you guys see a mammatus cloud, take a pic, send it to me with a date, time, everything. Agree or disagree? Agree. Great. Okay, so Kroor again did these simulations. So this is just a fun thing. I won't explain the physics, but we thought we could sort out the physics in a small way, and we made this movie where the top was cloud and we created mammatus clouds in the computer. Yeah. And this is another class of clouds. This is the last thing I'll tell you. It's called asperitas. It is the newest cloud in the cloud atlas. It's only 6 years old. March 2017, it was first classified as a new kind of cloud. Iske pehle, like the previous cloud who got classified was like 40 years or 50 years before then. So this is a, very rarely they add a cloud to the type of cloud. So this is in the World Meteorological Organization. It's been given the name asperitas. And you can read this. It's characterized by localized waves, blah, 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 as if you viewing a roughened sea surface from below. So this is again like serendipitous, but not rare. So you see this mammata, it really looks like a turbulent ocean, right? Like when you're seeing it from below. And this we think is a kind of variant on the mammatus. It's a kind of mammatus cloud, but when the wind is blowing in one direction. So we did that. We put the wind in one direction and we did this mammatus simulation again with the addition of a wind. And I don't know whether you'll agree, but it's kind of aspiratus. Agree or disagree? Great. Great, great, great. So before I end, I want to thank everybody I've ever worked with. I didn't bring all their photos, but this is my present group and you guys can talk to any of them if you are interested in these problems. And I think Rajeshi today explained many things for you, right? In the experiment. So the conclusion is there's a moral, like do science, do math, not compulsory, but try to do that. And think of climate science as a career option because there are big open questions at every level and stage. I just wrote down a few questions for cloud. We didn't even talk about climate change or what's going to happen. We just talked about how raindrops grow bigger. That's all. Thanks for your attention. She has to tell you. There's a question here. Can she ask? Yeah, go ahead.
Ma'am, is there a particular reason why it's usually considered that black clouds reign in the white?
Okay, the basic reason is that the bigger it gets, the more light gets scattered from it, right? Okay. So like it doesn't come down very easily. So that's kind of a ballpark reason.
And also the clouds that you showed here.
Also, the clouds that you showed here at the end, they had in the kind of the roughed areas, they had different colors. Again, that is because of the scattering of light again.
Yeah, so like somehow mammatus, right? It comes in the evening. It's very frequently seen in the evening. That's why you see, I mean, at least in India. So you see like sunset colors on it. Yeah. Any other?
Ma'am, you mentioned that Reynolds number is the ratio of inertia to viscosity. So if Reynolds number is very high, then it's more turbulent. So how is, if there's more inertia, then like how are they more turbulent? That seems.
Okay, so it's not a very intuitive thing that happens. Okay, but this thing, we can get it through some mathematics. In other words, like suppose I take honey. Honey has high viscosity and it has a low Reynolds number therefore. So like it's very hard for me to imagine honey being turbulent, right? So like what happens is, suppose I pass it through a tube. So I pass honey through a tube. And it's not going to go turbulent. I put high pressure here and force it to go in. So it will take a velocity profile which looks like a parabola. And that is a laminar case. Okay, but suppose like now I take this, instead of honey, I replace it by air and I push it with enormous pressure. Then what happens is that air, this parabolic velocity profile, it becomes unstable. So you can find that out by doing the stability analysis or trying to study the stability of this thing. So in other words, you know that stable means bottom of a hill, unstable, bottom of a valley, and unstable means top of a hill, right? So it's like at some Reynolds number, below some Reynolds number, the stable solution is the laminar one and the unstable guy is turbulent. So even if I put honey and I start jumping like next to the pipe, I can't make it turbulent. So even if I disturb it a little bit, it will come back to laminar when the Reynolds number is small, and the opposite will happen when it's turbulent. So turbulence is actually very, very counterintuitive. Like, you know, if you imagine that, I mean, we learn from Newton's laws that force is equal to mass into acceleration, right? And I'm giving like high pressure here and low pressure here. So I'm giving force in this direction. Then why aren't you walking in that direction? Like, why are you doing all this vertical and very disturbed behavior? It's like, I mean, teachers pushing a bunch of naughty children, right? And when they want them to go in one direction, these are going the other way. So it's actually a counterintuitive solution of the equations. But then like that becomes the valley above a certain Reynolds number. Is that okay for you?
Thank you, ma'am.
Yes.
Is that similar to aspiratus?
Yeah, it doesn't, it may or may not be, but you look in the cloud atlas and see if you can submit this. Yeah, it's nice. You have a mammatus. Oh, you took it on the same day. Where?
Near my house. I was coming back from.
And you're in Bangalore.
Yeah.
Oh, cool.
Yeah, I could.
Oh, cool. Yours are better than this.
I had more. I took because I knew it was something I had not seen before, so it
Oh,
started.
cool.
Like, I took like some 20 pictures of the same thing in different time periods. Yeah.
Amazing. So send them to me.
Okay.
And if you have the timestamp, send it.
I do.
And then I'll know like how it evolved.
Anyone else?
Yes.
Water droplets are too heavy than air. So when you on clouds are too far away from our earth. So when they are falling, why they don't hurt us?
Oh, they don't.
Why air is not able, since air is lighter than water droplets, so we conclude that it should not be able to handle them. So why still they are not hurting us?
Okay, I think it's just because they're not that big yet, and they're not falling from that great a height yet. Because like you've seen ice, you've seen hail, those are rain formed at a much, much higher height. And those things are actually big, right? Those ice things, those can actually hurt you. Yeah. So it's just a question of size and velocity. So you can calculate the terminal velocity and measure the force. These terminal velocities will be like tens of meters per second. So if a small thing comes at 10 meters per second, it may not hurt you. Like I don't know about the human physiology, like how many newtons I need to feel hurt. So, but you can read about it. Questions? Thank you, guys. It's been fun talking to you.